Hi, everyone. Good morning, and welcome to the ECE Colloquium today. And this is the second part of our 15th annual Dean W. Lytle Endowed Lecture Series. I'm Mariam Fazel. I'm a professor in the ECE department and chair of the Lytle Lectureship Committee. So hopefully many of you were able to attend yesterday, the first lecture in the Lytle series. For those who were unable to attend, the Lytle Lecture Series is our department's premier annual event that features renowned speakers that will visit our campus and give talks in the areas of signal processing, communications, machine learning, and control. Today's seminar follows yesterday's excellent talk by Professor Anca Dragan, and it's a deeper dive into robotics algorithms that take humans into account and interact with humans. So let me tell you a little bit about our speaker. We are very fortunate to have Professor Anca Dragan, who's a professor in EECS at UC Berkeley. She got her PhD from the Carnegie Mellon University and actually worked with Professor Sid Srinivasa as her PhD advisor, who's now a faculty member in the CSE department here at UW. Her research has won many outstanding awards, including, it's like really too long to list, but from NSF Career Award to the Sloan Fellowship to the MIT TR35, that is the 35 Technology Review Award to people under age 35. She's won one of those. The Okawa Award, and the Presidential Early Career Award known as PCASE, that is the highest, one of the highest honors of NSF. So please join me in welcoming Anca, and we are excited to hear her talk about the human-robots interactions.
Thank you. Hi, everybody. Welcome back. If you were at my talk today, that was for a very broad audience. This is a lot more kind of nuts and bolts and a lot less polished. You're going to just kind of hear my raw rants about human models. Why do we need human models? Well, if you think about the standard way we formulate robotics, here I have a little quad rotor. It needs to take an exit or whatnot, and we tend to formulate the problem something like find the robot policy that in expectation maximizes the robot's cumulative utility. But then when there's also a person around, even if all the robot has to do is still do his task but not hit the person, which is a very low bar, now the problem fundamentally changes, because now you can't really evaluate the robot's utility by just knowing its policy. You sort of have to know the human's policy as well, and how the actions that the human takes and the actions that the robot takes end up sort of gelling together. That makes interaction hard, because humans are complicated. So this is a quick video to sort of show this quad rotor thing. And this is from work with Claire Tomlin's lab. And we have a little quad rotor here, and we have a human being labeled human being for clarity. And to be able to figure out how to reach its goal and not hit Sylvia, this quad rotor is making these predictions about where Sylvia is going to go next, and then planning its trajectory to make sure it stays out of the way. So this is just for the purposes of avoidance. Interaction typically means more than avoidance. Recently, we introduced this cute little benchmark for collaboration that's inspired by the game Overcooked. So here you have two agents, a human and a robot is supposed to be the case, and they have to actually collaborate to make onion soup. So there's onions here. They have to go and cook the onions. They have to grab plates, and then they have to deliver at the soup delivery location. And it looks really toy, but it's actually task and motion plan. It's really hard for planners to actually solve this. But here's some humans playing together. And what I mainly, they grab the onions. They put them in there. And you'll see that they are sort of doing this kind of beautiful coordination thing where one of them grabs the plate, and the other one is like, okay, you grab the plate, so I'm going to get an onion and put it in the other pot. So they're sort of doing a bit of role sharing. And that's really nice. Now, what makes it hard for a robot to take the role of one of these humans is that you don't just have to avoid the other human, you now have to actually collaborate and coordinate with them, right? And so here's kind of an example that we saw from trying to get a robot to collaborate. It's a very, very simple thing, but it kind of portrays the kinds of things that can go wrong. So here, robot and human, and according to the robot, what should happen is that, the robot that's on the left grabs the plate, and then the human grabs the onion. Because, for the robot to grab the onion, then it would have to have a long way back. So that's just, it's like, this is the optimal thing to do. I'm going to go and grab the plate. You're going to go and grab the onions, which are right behind you. But of course, like, a person is right next to the freaking dish dispenser, so they're grabbing the plate, right? And now you have this kind of coordination mismatch where, they both go for the plate, and sort of the task gets delayed. So this is why this is hard, right? Even simple, small things like that. And so to be able to avoid humans and even more to collaborate well with them, it's really useful for these robots to have some sort of model of what the human's policy is going to be so they can take the right actions in response. So where does this model come from? It was really hard to write equations about people, so naturally, this is a place where we want to leverage data. We want to collect data about how humans act and sort of learn that human policy. And the question is, how? How do you leverage data? And a natural thing to do these days is to treat the person as sort of a black box policy and sort of throw a deep neural network at the problem that maps state or history of state, right? So X is state, but it could also be a history, to the action or probability distribution over action that the person would take based on supervised learning, based on the data. And so we did that with Overcooked. We collected a bunch of human data, humans playing. And then we learned a neural network. So we did some behavior cloning. And it worked kind of great. Maybe not surprisingly, you have enough data, things work out. So here's the policy. Now there's actually two robots playing with each other based on this policy. And you see that they're taking onions, they're making onion soup, they're delivering things, and there's coordination. Like, this one is hanging out with an onion, and this one grabbed the plate, right? Because it's just like, OK, if you're doing this, then I'm doing that. So there's a little bit of that coordination that we see in human-human collaboration as well. So that's cool. I saw that. I was happy. This is my student Micah's work. And then I asked Micah, hey, what do you think would happen if we took the same environment, but we just put a plate on the counter? There's a plate here now. It shouldn't really change things that there's a plate on the counter. But of course, this doesn't really end up in human data very much, because in human data, you'd end up with a plate on a counter if someone messed up and grabbed the plate and realized they don't need it, like it was a coordination failure, right? And then they're like, oh, I have to put the plate back, I have to go and grab the onion. And so here's what happens, and I'm going to play this again. Let's see. Whoops. I'm going to play this again. They're doing stuff. They're going through the motions, but if you look closely, it's all nonsense. None of it makes sense anymore. This one just delivered a plate over here on the counter instead of giving it in the gray area, which is the delivery area. That's how you actually gain points. This was just wandering around with soup. I don't know. Doing stuff. So they're not actually delivering the soup anymore. This is why? Because, oh my God, there's a plate on the counter. We do not know how to deal with a plate on the counter. The whole problem is so different now. So, this is the stuff you have to deal with. I took humanity's prime example of behavior cloning, which is GPT-3. If you don't know what GPT-3 is, just this ginormous language model that's pretty magical in many ways. And I asked GPT-3, Anca throws the ball to Chris, who throws it to Lucas, who has the ball. GPT, magical, because you just have to get it to pretend like it knows something, and it will actually know that thing. It's an amazing feature. And so GPT is like, Lucas has the ball, great. And then, I'm sneaky. I like to put plates on the counter. So I tell GPT, okay, Anca throws the ball to Chris, who throws it to Lucas, who has the cat. And GPT says, Lucas has the cat. Like, okay, why? Because he caught the ball that Anca threw him. Glorious. So even GPT-3, our humanities prime example, right? It's easy to get it to be a little brittle and confuse it up. So I think it's not unfair to say that high-capacity models can be brittle under distribution shift. I don't think that's controversial. The interesting question is, does that matter? Does distribution shift occur in human-robot interaction, right? If we use models of people and get robots to interact with people based on these learned models, are we going to have distribution shift? And what I'm learning is kind of yeah. And part of the reason is that what people do depends on what the robot does. So robot actions end up inducing distribution shift in their ultimate policy, but at the very least while learning the policy. So why do human actions depend on what the robot does? Well, it's easy to see here. This is an example from yesterday. We were talking about driving. I have an autonomous car in orange, and it needs to make predictions about where the person will be to make sure it doesn't hit the person. And it might predict that the person goes straight, which is correct if the car actually keeps driving in the right lane and slows down and merges behind the person. But if the car does something different, if the car starts nudging towards the person's lane, then that person will do something different, which was they will slow down, right, and let the car go. So human actions depend on robot actions. And so what that means is that you have this black box policy that you've learned, but when your robot acts, it changes the distribution of states that you're evaluating this policy on. And it might happen with the final solution, or it might just happen as you're doing reinforcement learning. We're planning up against that human model to figure out, okay, if I were to do this, what would the person do? If I were to do this other thing, what would the person do? So you have to explore different options. And that means querying the model on a distribution that is outside of what you've trained it on usually. So high-capacity models can fail on the distribution shift, and I think that planning and reinforcement learning, when you're using these models for the human and best responding, tends to induce distribution shift, so that's a problem. And so there's an alternative, and that's the alternative I talked about yesterday. But what I want to tell you today is that everything that I talked about yesterday is nonsense because it assumed that people are rational, and that's just bogus, okay? It led to magical things, and if you haven't seen the talk yesterday, you can watch it on YouTube. Magical things happen when you assume people are rational, but it's also wrong, and that also leads to some issues. So let's talk a little bit about that version. So the idea, the alternative is that instead of saying people are these black boxes, they can take arbitrary actions, is to recognize that most mappings from state or history of state to action are bogus. They're never going to happen. A human would never, most of these policies, a human would never, ever execute. Because human actions are structured. How are they structured? Well, it's typically because we behave the way we do because we have things we want to achieve. We have these things called intentions. So the way this person walks is a consequence of them wanting to get to the door. Not necessarily they walking in a perfect way to get to the door, but their actions are driven by this underlying notion of what their intent is, and then there's cognitive processes that help turn that into actions. And a natural way to think about intent is to formalize intent as utility. The person has a utility, a reward, a cost function. Someone was asking about satisficing and constraints. You can think about it that way too. But some notion of an objective that the person wants to be good with respect to. And that objective is parameterized, right? We have to commit to a parameterization, and we're going to call that parameterization theta h. Theta h, h standing for human, could be, a lot of the times we think of it as, well, there's these sort of features of state and actions that people might care about. Usually we think of it like, I want to make progress towards a goal, I don't want to hit stuff, et cetera, et cetera. And theta h might encode the trade-offs that people make between all these different competing interests, all these different sort of smaller objectives that they have. But theta h could be weights in a neural network. Theta h could be just the goal location. Theta h is just, it depends on the problem, I guess, how it's useful to parameterize it. OK, so once you have a theta h, the thing that you can do, the easiest thing you can do is assume that human actions are the optimal thing to do under that utility. And this is something that dates back to 60s, to Kalman, and has been adopted into AI by folks like Ng, Anna Beal, and Stuart Russell. Nathan Ratliff did maximum margin planning. And essentially, it basically says, look, if I know theta h, I can tell you what UH is exactly. It's whatever UH is the argmax of the Q value function induced by theta h, right? So that's a very, very simple human model. Of course, in economics, people have been thinking about this for way longer. So in economics, already in the 40s, probably dates further than that, but I kind of attribute a lot of these things to von Neumann. And so, von Neumann said, let's think about humans as taking actions that are max utility. It's not in the sequential setting necessarily, but it's the same idea. AH, the human action, is the argmax of some utility. Now, shortly after, a decade after, Lewis and Shepard came along. And they said, no, 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 no. Clearly, people don't just do the optimal thing. Are you kidding me? So we have to allow for a little bit of noise. We have to allow for human error. And the way they did that was with this Lewis-Shepard axiom of choice, which says the probability of an action, it's not 1 if that's the optimal action. It's sort of proportional to how good that action is, and in particular to the exponent of the utility. And that was brought over into robotics and AI land by things like Bayesian inverse reinforcement learning, by Maxent IRL, in CogSci by folks like Chris Baker with Josh Tenenbaum. And to this day, that's sort of the standard model you'll see in many papers on inverse reinforcement learning, in many papers on sort of learning reward functions from human preferences, for comparisons, and so on and so forth. And before I kind of, excuse my language, crap all over this, despite the fact that I've written like 30-something papers that use this, right? So I'm a big fan in many ways, but it's also wrong. Before I tell you all about how it's wrong, let me just kind of quickly summarize the things that I love about it. First off is that you can derive this model in a very principled way. There's many ways to derive it, but here's the one that I like, is you just have to say that you expect the person to take actions that are epsilon optimal, right? In expectation, they'll have the optimal Q value minus epsilon. And then outside of that, you don't want to assume anything, so you're gonna, in the null space of that, maximize for entropy. And if you solve this, right, to the KKD conditions, blah, 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 you get this Boltzmann distribution. You get that the probability of the action is proportional to the exponent of the Q value. You get a coefficient beta that's related to that epsilon. So it's really beautiful. If you set epsilon to 0, you get this kind of perfect human, perfectly optimizing the Q value, and that corresponds to a beta going towards infinity. If you set beta to 0, that corresponds to a random person, so completely noisy, erratic, no structure. Okay, so that's one thing. It makes a lot of intellectual sense that you would do this. And then enables you to make predictions about how the person behaves. And the idea is, you don't learn the distribution over actions directly. What you learn is these theta parameters that are hopefully much smaller than how you'd have to represent the full policy. And that theta h, once you know it, that dictates what the probability over action will be. That's sort of the idea. Now, the robot is not acting according to this policy. A lot of times when you see inverse reinforcement learning, it's used in the context of teaching robot tasks. That's not what I'm talking about. I'm talking about this as a model of how the person behaves. And then what you do is you compute a best response to that model via planning or reinforcement learning. And yesterday I also talked about how you can think of it as strategic rationality. So now we're in a game theoretic sense, and we think of the human and the robot as arriving at policies that are best responses to each other, and therefore at a Nash equilibrium. Sometimes we work with Stackelberg equilibriums. Those details are not important. What I want you to think about here is that you assume that the person is this noisy rational. You learn the theta parameters, and that's the robot's model of how the human works. And one example that I gave yesterday that I think is the perfect one to really highlight what I think the advantages of such a model are, again, before I crap all over it, the thing that we can all appreciate about this model is that it has an enormous amount of ability to adapt and make good predictions out of distribution. So this is an example, again, that I talked about yesterday, where we put a car at a four-way stop. The car had learned a model of the person from human data, so it learned these parameters, theta h, that trade-off, obstacle avoidance, efficiency, et cetera. So it kind of knows the person tries to be optimal with respect to being efficient, but also not hitting stuff. And we gave the reward function to the robot, which is in orange here, of get the person first through the intersection. You get a reward for how fast the person goes through the intersection. What do you do? Go. And then we did MPC to optimize the robot's policy for that. And the robot doesn't stay there and wait for the person to realize they can go. The robot doesn't just go really quickly through the intersection. It's another kind of strategy that could work. The robot, I kid you not, starts inching backwards from the intersection, which, as I mentioned yesterday, the first time Dorsa came to me and she's like, I think there's a bug because this weird thing happened, and I thought about it, and then I really got very excited because this actually makes a ton of sense. It's just not something that I would have thought about. It's that if I remove myself as a potential collision threat, the person who cares about being efficient but also about not hitting stuff is more likely to go through the intersection. Now, why am I talking about this in the context of loving the noisy rationality assumption? I want you to contrast this with behavior cloning from a lot of human data. By the way, I should say, this works with people. They go faster through the intersection. Then you can look at human-robot interaction researchers. They design cool strategies that are called the backup strategy, not for cars, but for robots to kind of signal to you that you should go first as you're going through a door, stuff like that, right? So this is really cool in my world, and I have a ton of appreciation for this. And if I think about trying to get this with behavior cloning, not only behavior cloning for the robot wouldn't work because you never see people act this way, but also behavior cloning for learning the human model wouldn't work because you never see people respond to someone else acting this way, right? If no one backs up at an intersection, I don't have data for how people respond to that kind of action. And for the robot to realize that this is the optimal action for its reward function, it'd have to have a good understanding of how the person would respond. If that's not in the data, that's an out-of-distribution query, and chances are your model will have no idea what to do with it. But noisy rationality doesn't have that problem, right? You can train it all on it's like this model is trained on highway driving. This model is trained on how people drive when they're on the road, and it learns these trade-offs about efficiency versus staying on the road versus blah, 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 and you can just plug it in at a four-way stop, and it's just fine. It's never seen four-way stops before. So noisy rationality, yay. But then again, people are not rational. So after many papers where we said, oh, this is a great way to treat humans, blah, 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 we're starting to run into the limits of what you can do with this kind of approach. So here is the Atari game of Lunar Lander, and this is data people playing this game. And the goal, you couldn't tell, but the goal is to land in between the two flags. Land, not crash, in between the two flags. And we were doing this little project where we wanted to assist the person with this, and we didn't know where the flags were, so the robot had no idea where the person is trying to land. So we were trying to infer that from the human action. So that's the theta H. You're looking at human data. You're trying to infer that. And it was very, very wrong. It was usually overshooting the goal to the left or to the right. Because when you think of these actions as noisy rational, that's what you get, right? So you infer the wrong goal, and then you really try to help the person get to the wrong goal, which is bad. We also tried this in Overcooked. In Overcooked, it turns out that if you assume that people are noisy rational, your cross-entropy loss is on par with random. Random. So this is, soul-shattering for someone who spent many, many years actually, leveraging this model. It's a bad model for people in many cases. Now, that doesn't mean it's a bad assumption. I think, the way I resolve this in my head is that a lot of the times, assuming a bad model still leads to a correct response for the robot, so it's okay. But sometimes it doesn't, and that's a problem. And if you think about human decisions outside of a robotics contest, there's all sorts of decisions that people make that tell you that they're not acting according to, the rational laws of economics, right? People, for instance, I'm a mom now, people decide to not vaccinate their kids for measles. And that's, scientifically, that's not the correct thing to do. But nonetheless, that's how people act. This shouldn't be surprising because in the 70s, behavioral econ came along and basically said people are not rational, they're not noisy rational, they're a pile of heuristics, okay? They're a pile of all these different cognitive biases. And since then, since the 70s, there's been this deluge of possible cognitive biases that have been observed. Many of them have a name. Some of them don't have a name. They're just there in experiments that people have done. Most of them are things that people have observed, but we don't have any formal understanding of. And on the left-hand side, my robot's sitting there being like, I need probability of UH. What's the probability of UH? That's what I need in order to do my task. What am I going to do with a list of 170 whatever biases that people have? And so trying to formalize each of these biases and adapt the model to account for that feels like an insane wild goose chase. We're not going to get anywhere with that approach. So now what? Because if I don't structure the model, I have this brittleness out of distribution that the robot sometimes exploits. If I structure the model, it's wrong, and I can run into issues. So now what do I do? And we have about half an hour left together. And what I want to share with you now is some very recent work that we've been looking at. So this is very much more raw and exploratory. And I would roughly categorize it into sort of two buckets. There's work that we do that I'd say is very practical, but kind of boring, but practical. Boring in my mind, right? So it's just a personal judgment. And then there's work that we do that I find very intellectually stimulating. I have no idea if it's practical. You can tell me after you listen to this. Okay, so real quick, I've mostly focused on the second bucket, but for the first bucket, about practical, let me give you a flavor of the kinds of things you could do to sort of bridge these worlds and sort of get more robustness. One thing you could do is to get more leverage out of the data that you're collecting to robustify sort of a model that is an unstructured model, right? So This is, I just have one slide on this. This is from a paper that we're presenting at NeurIPS. It's called UniMask. And the gist behind this paper is that the way people train large language models that ends up working so beautifully is by, one way to think about it is this randomized masking, right? You sort of take some text, you occlude some part, and you ask the model to fill in the blanks. It's a very weird kind of task for text. Because when would you want to fill in the blanks in the middle of some sentence or whatever? But it's actually a very natural way to think about many, many, many sequential decision-making problems, right? A lot of the times we're interested in prediction of humans, like my quad order was doing, and or Claire's quad order really was doing. And so, so that's, I get to see the first part of a trajectory. I want to fill in the rest. Sometimes we do goal conditioning. I'm here, and I want to get there. What's in between? Sometimes we want to condition, like decision transfers on good, getting a good reward. Give me the states that I have to go through. Waypoint conditioning. There's a lot of different tasks that actually naturally fit into the structure of corresponding to one of these masks. And so what Micah decided to do is collect data, and instead of just training behavior cloning directly on that data, train a model to basically do randomized masking and fill in random bits of trajectories. Okay, so just any kind of mask, any kind of bit that you can occlude, bam, do that and get the model. So this is self-supervised pre-training, and then fine-tune that model for behavior cloning specifically. Turns out this gets you a good amount of robustness. So that's one thing that I think is like, yeah, you can do it. You should probably do it in practice. If you're going to do behavior clone, you should probably pre-train this way. I don't know. What have I gained intellectually from this? I don't know. But that's what I mean by it's practical. It's called UniMask. Yeah. The other thing, again, a very obvious idea, is you pre-train using something like noisy rationality or some approximation thereof. And so, here's overcooked. You can do self-play. That gives you a pretty good approximation of optimal behavior. And then you initialize behavior cloning with that. And so it basically, optimal behavior serves as a prior, but then you fine-tune that with human data. Again, greatly, greatly robustifies behavior cloning. And I have some graphs, but I don't think it's useful to actually look at that. That's the gist of it. So, these are some practical things you can do, and we're still exploring things in this area. Let me talk about the interesting things that you can do. So, here's what I find interesting these days. I'm going to start with a very unpopular opinion. I am one of the old curmudgeons now, right? I'm more senior faculty. I get to say unpopular things. I am concerned that we are in a world where we take pride in thinking less and throwing more data at the problem. And we're like, I didn't have to think. I could just throw data at it, and it worked out great. So my little unpopular opinion was that, in this one piece of work, we did a little bit of math, just a tiny bit more math. And it bought us the equivalent of a very large amount of data. So let me share a little bit about that. This is, again, an Overcooked. This is Cassidy's work, and really Cassidy's idea. So he observed that in Overcooked, and probably in real life, yes, there's optimal actions. People don't take optimal actions. For instance, it's optimal here to go counterclockwise, but people go clockwise for whatever reason. But once they go clockwise, they keep going clockwise. It's not like, they take a step, and then they're like, whoa, now I'm going to turn around and start doing it the optimal way. So people aren't always optimal, but there seems to be some systematic way in which they're suboptimal, right? And it's probably described by a combination of 50 biases from behavioral econ plus 5 that aren't yet discovered. I don't know. But there's some systematic suboptimality. If you look at Boltzmann rationality, this noisy behavior, noisy rational behavior model that we've been talking about, it basically, when you're trying to, so it says the probability of a trajectory is proportional to the exponent of the cumulative reward. And when you're trying to predict the next action AT condition on history, the Markov property comes in, and basically it just depends on the current state, right? So what I predict you'll do next only depends on the current state, not on all the actions you've taken so far. So it's very hard to capture this notion of once you deviate from optimality, you're going to do that in some sort of systematic way, because I forget all the history. And so Cassidy had this very simple but useful observation. Oh, I don't know about useful, but very simple observation of you won't be capturing systematic suboptimality when you predict distribution over trajectories or over actions. You have to couple action choices over time by predicting distributions over policies instead. Okay? Because policies are the things that actually capture couple these effects. And so we can basically modify this Boltzmann rational model to say, no, it was wrong to think of it as predicting, as sort of being kind of independent of the state. We should think of it as a distribution over policies instead. So a policy, the probability of a policy is proportional to the exponent of the cumulative return of that policy. And then when you predict the next action, right, given your distribution, you're going to actually take the history into account to compute your posterior over policies, and then you're going to marginalize that over policies to figure out what action you're predicting the person to take. Real quick example here, very toy. The person is picking up apples. They get, reward 1 for every apple they pick. And if we look at Boltzmann rationality in this little toy environment versus the Boltzmann policy distribution, right? And how they're making predictions, you kind of see that as the person sort of decides to go counterclockwise, right? And you observe that, the BPD, the Boltzmann policy distribution, sort of updates its predictions, its understanding of the policy. It's like, OK, this is probably how you're going. Whereas this one, right, the Boltzmann rationality, the standard model, is just like, well, I haven't, I can't take that into account. That's just in the same state. I'm going to make the same prediction as before. And then when the person returns, same thing. So the way it's difficult. It's already difficult to compute the Boltzmann distribution. But Boltzmann policy distribution is a lot more difficult to compute because it's a distribution over policies. And so we do implicit variational inference here. We use this kind of pretty standard trick of you have a latent vector z, and in a sense you train this policy conditioned on z to represent the Boltzmann policy distribution. And sort of in the paper we derived the right training objective for this, so that basically this latent distribution over z captures your distribution over policies. This is a bit of a visualization, though, of in that domain, right? You start off in this sort of whatever this two-dimensional latent space is. We start off with some distribution, and as you observe more and more, you're sort of shifting your probability mass around. In practice, we don't actually do inference over z directly because that's very computationally difficult. So we throw a transformer at it to predict actions directly based on history in the BPD. OK, and so and I should clarify. When I say we throw a transformer, we don't throw it at the real data. We throw it at data generated by the sampling from the Boltzmann policy distribution and training the transformer to approximate the inference for us. OK, the graph I can show you here is that while the standard Boltzmann rationality is kind of on par with random, if you look at cross entropy loss, this is not only significantly better, but it's starting, okay, it's not the same, but it's starting to get close to behavior cloning. This uses a crap ton of data. This uses barely any, it's just like within the episode adaptation. And then that makes a difference when you start to actually do collaboration, right? So in collaboration, you're noticing, we're noticing really good performance, where if you use the Boltzmann model, you don't collaborate very well. This is what happens with the BPD. If you just imitate human behavior, that's not good either. And this is a really cool baseline, is like if you actually best respond to that behavior clone model with a lot of data. So that's sort of the state of the art. So basically, the takeaway here is that this is still the best. It's learn, throw a lot of data at the problem, and then do RL against that model to figure out what the robot does. This kind of gets closer and does not use all of that data, or most of that data. And when you put a plate on a counter, it kind of does OK. This is my new bar for things. Can I put a plate on a counter and have it not completely bark? It's like delivering the soup. You'll see it in a second. It actually like delivers the soup, which is like yay, and doesn't completely shatter. It delivers soup. So that's my unpopular opinion about how a little bit of math, right? It's just like, don't do it over trajectories. Do it over policies. Right? It's just that little change of acknowledges very simple fact about the model ends up actually getting you remarkably close, in my view, to the performance of imitation learning. The other line of work that we've been pursuing is somewhat similar, but yeah, I've had a baby. And so I now look a lot at developmental psychology to sort of see what I would expect. And so I geek out reading Alison Gopnik's work and just a lot of other people's work on what babies do at various times. There's this thing that babies don't do well, and they don't do well for a long time into toddlerhood and even as children. So let's watch this video to see what I mean. Oh, we don't have audio. Okay, never mind. I wonder if I can.
Play-Doh. And if I were to ask
Can
Mommy,
you hear this?
what do you think she would think was in here? What do you think she would, if I asked Mommy what was in here, what do you think she'd say?
Play-Doh.
Play-Doh? And what if I asked Sophia what was in here, what would she say? Play-Doh. Okay, open it up, see what's inside.
Okay, so she thinks it's Play-Doh, and she thinks that Mommy and Sophia also think it's Play-Doh. That's the TLDR so far.
What was it? Coins.
Coins.
Okay, let's put them back. Now, if I asked you again, what would you say is in here? Coins. What if I asked Mommy what was in here? What do you think she'd say was in here? Coins. What if I asked Sophia? What would she think's in here? Coins.
Okay, so this is called the false belief test, and children fail the false belief test, right? They think that everyone else has the knowledge that they have, right? So if I know it's coins, Mom would also know it's coins, and Sophia will also know it's coins.
It's interesting on that, though, because she shook the can every time she responded to the question. She said, what do you think Mom would think in there? And then she shook it and she said coins, almost as if she expected Mom to shake it and then conclude. Right?
That it's coins.
Does she have a false belief, or does she actually change her mind about how Mom is going to attempt to answer the question?
Yeah, so the comment is, maybe there's something much smarter happening in children where they answer the question based on actually imagining that Mom will come in and Mom will shake the thing, and so it's totally possible. There's many versions of the study, and it's I mean, okay, let me actually skip I'll skip over this. This is perspective taking.
The adult and child.
And it's the same thing, but let's skip that in the interest of time. I will pick up on that question or comment, though, to say there is controversy in the psychology community about this topic. Do children really fail the false belief test, or is it about how we ask the question? Okay, and so we don't know. There's been many ways these studies have been run, different ways people ask the question, and kind of pretty consistently, for the longest time, it's been established that until 6 years old, or so 4 to 6, 4 years old definitely, that children will fail the false belief test. Okay? But then this Tomasello group did this other kind of work where well, let me see how I can describe it real quick. 2 boxes, there's an object in there, the person sees the object, the person leaves the room, the object gets moved. The person comes into the room and starts looking for the object. The child realizes that the person is looking for the object. So they argue that if children didn't understand false beliefs, they couldn't do the intent inference to figure out that the person is looking for the object. Because if you're really convinced in your head that the person thinks that the object is over there, you're not going to understand the person starting to look over here as they're trying to find the object. Okay? I know this is like theory of mind on steroids, but that's and so this group is saying it's about how we ask the question, and if we tap into the children's like wanting to be helpful and stuff like that, maybe they can't verbalize, they can't answer the question, but they understand it latently because they're tapping into that. So there's drama now about the children actually failed the false belief test. My claim, though, is that robots fail the false belief test. Okay? So when a robot looks at a parent not deciding to not vaccinate their kid for measles, for instance, I really don't want that robot to infer that the parent doesn't care about their kid or hates their kid or something, right? It's really that the parent has a different belief than, I don't know, the robots in this case, right? The robot might have read a bunch of science that says that vaccines are totally safe, blah, blah, blah. And then the parent might have read a bunch of articles that say that vaccines cause autism and you should be really concerned. And so it'd be really great for robots to look at these suboptimal they're suboptimal. I don't know if they're suboptimal, but let's assume that vaccines don't actually cause autism, blah, blah, blah. It'd be really great for a robot who, believes or has an estimate about facts in the world, and that estimate is that vaccines don't cause autism, to not look at human suboptimal behavior and make inferences like, oh, maybe the person doesn't like their kids. It'd be really great for the robot to understand, as children might or might not be able to, the debate is still on, that people might have a different belief, and that false or different belief might be what is driving their decisions. And so I got really excited about this, I'm sure it's not a perfect explanation of what happens. In fact, it's not a perfect explanation of what happens, but it seems to be a more useful one than noisy rationality, which is let's give people the benefit of the doubt, and let's think of people not as hopelessly irrational, but as really trying to do the rational things, but under false beliefs or different beliefs than those of the robots. So what does that mean? It means that we've been taking the Bellman update and saying we can't really assume that of people. We can assume that, but under an estimate of state, under an estimate of dynamics, under an estimate of their own reward parameters, their own preferences. There's this cool example of you don't know if you like durian fruit until you try durian fruit, and you either love it or hate it. So you live your life and you're still learning about the stuff that you that you want. So I can't assume you know your preferences, okay? So an estimate of their own preferences and maybe a couple other things, and then these estimates might actually evolve over time, right? As people receive more information, they understand more and more, and they change. So 5 minutes, I want to give you a quick example of estimate of dynamics and accounting for that. This goes back to lunar lander. So here, if we do inference from sort of rational people, essential or noisy rational people, normally we think of, okay, there's a person, they have theta in their head, they act. I'm going to assume that they act in proportional to x of the q value according to theta. That was the noisy rational model, right? So this is the standard way we would do it before the false belief thing. The q value satisfies this, and then when we see them act, we can update our belief about theta. That's how we used to do things. Implicitly, right, we've observed that implicitly, what we're saying is that there's parameters eta of the world. The person knows that. So whatever the robot knows about how the lunar lander's physics are, that's what the person knows too. And when they're computing their Q value, they're using the correct parameters of how the world works. And that's the policy, and I'm doing the update based on this. But what Sid Reddy said was, wait a second. People have intuitive physics models. They don't actually know exactly how the world works. And so they have some like eta hat estimate. And that's what they're using in here. And so now we have to look at the sort of their actions in terms of inferring not just theta, but eta hat. We have to account for eta hat as being something that we don't know. And we simplified this, blah, 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 many approximations, but the bell rang, so I'm not going to go through that. But basically what happens is the person commands the lander to go somewhere. Instead of executing that, Sid had the lander look at passing it through, instead of executing the real dynamics, which would crash, Sid had the lander pass it through this learned internal dynamics model, where lets the person think they're sending the lander according to their intuitive physics, which, by the way, in our estimates is sort of that people don't account as much for inertia. They underestimate the thrust power, stuff like that. And that's what it seems to be the case. That I don't know what happens in people's heads. OK, so then the robot actually computes the action to take to actually send the lander where the person thinks that the lander will go, instead of where it will actually go if it executed that. And then it's not that it's perfect, but like people land the thing, right? And you go from, this is point mass control, but you go from crazy all over the place trajectories to actually success. And then we're currently working on enabling robots to account for people learning their theta hat over time. It's not like there's a fixed theta hat. As you interact with this system, as you observe how the world responds to your actions, you learn more and more. And so the person is teleoperating the robot. They don't know inertia. They don't know drift. But they update this understanding over time. Again, we threw a transformer at this and figured out dynamics of how people update their understanding, and then figured out, OK, the robot is actually influencing what people see. They're influencing the observations. And then, therefore, the robot can influence the learning that the person has over what these parameters are. And so we learned the dynamics, and then we optimized the robot's policy to be informative to the person about the dynamics. And we saw that people can control the thing eventually on their own better. Right? So it's not just, OK, I am transforming what you're doing. It's actually, I am now, over time, getting you to be familiarized with the system. And at some point, I can really wean off my interventions and let you pilot this thing yourself. OK. Maybe I'll stop here. We also looked at estimates of states. But I don't have time to talk about this. There's a lot of things here about how you can give people synthetic observations that compensate for their suboptimal perception system, estimating states in the incorrect way. But sort of the bottom line is, maybe it's useful to not think of people as completely unstructured, but not rational or paper over rationality with noise either. Maybe it's actually really useful to think of people as operating under false beliefs and try to understand what these beliefs are and how they change over time. That might give us a more lucrative model than noisy rationality, while also maintaining a lot more robustness than unstructured models. And so maybe that means that there are mathematically elegant, intellectually satisfying for me ways to think about human models that perhaps also make models more robust and reduce sample complexity. And that's sort of my rant about practical versus interesting ways to think about human modeling these days. And there's a lot more work that we've done on this kind of topic that you can look up. I'll leave that here for a bit. And with that, I'd like to thank the Interact Lab, and especially Cassidy, Sid, Thomas, Micah, and collaborators whose work I've highlighted in this. Thank you.
Okay. Thank you, Anca, for a great talk. Are there any questions? Can raise your hand, and we can repeat your question down here. Yes.
Hi. Quick question about the false belief tests on kids. If the kid gets exposed to the question over time, do they learn it, even if they're 1 or 4 or 6 years old?
Can you say that again? Sorry.
If the test is run multiple times on the kids, on the toddlers, do they learn to finally identify that their belief is incorrect?
No, not. They will even.
Repeat the question.
Okay, the question, as I understood it, is if I show the kids what, mama thinks there's coins in there, and they realize that what the mama's belief is, are they able to correct? And the answer is no. They will, until they're 4 or 6, no matter what you do, they're not ready to explicitly have this concept of false beliefs. Tomasello's arguing that implicitly they have it already, whether you demonstrate or don't demonstrate. But that seems to be the idea with kids. They'll just keep on. It's related, maybe another way to understand more about kids this way is that they also don't understand object permanence until a few months old. So when they get born, they think if something goes away, it's gone forever. And so their brain is just not ready to kind of deal with that concept yet. And you'll see that in their actions. Yeah.
Any other questions? Yes.
So you talked a lot about the core insights of your work being mathematical in nature, and neural networks provide something a little bit peppered benefit, but not the core thing. And I'm wondering, how would you articulate what the value, what the role of those big data models is in the work that you do? What's the benefit there?
Yeah, and the honest answer is, I think it's for us as a community to figure it out. But because you want to have systems that, as you get exposed to more and more and more and more data, they can actually do well. But there's a couple. So there's a number of ways to think about this. You can think of those models essentially being able to provide to consume the mathematical assumptions, but then be fine-tuned with more and more human data. So that's one way to think about it. So far for us, besides, that was more in the sort of practical side. In the things that I find more fascinating side is more of a take of, you'll always be running this computation of this Bellman update, blah, blah, blah. So that will always be happening, whether you do it with a neural network or not. I don't really trust neural networks to be able to do that very well. But there's progress in that area. But then where a lot of data comes in is in sort of learning the person's dynamics assumptions, is in learning which you have to be careful about, is that if you make the dynamics model a giant neural network, then you can pretty much explain any policy by inventing a dynamics model. But the observation that we have is in a sense that you can put this prior on the dynamics model, which is, it's somewhat close to the physical one. And that maybe is, a better way to model what's going on, that the person has this wrong dynamics model acting approximately optimally based on it, than trying to sort of, start with a rationality based on the ground truth model and then fine tune with data. Because that network will have to sort of implicitly uncover that, then the fine tuning, that the way you deviate from rationality is by like doing Bellman updates on the wrong model. And that's hard for a network to learn. So that's kind of what I'm going with this like last part of the talk, is that if you find the places to throw data at, then maybe it's much easier to explain human behavior. If you're right. And if you're wrong, then, Yeah.
Has this kind of the idea of people not just being noisy rational, but having kind of rational suboptimal behavior, has that been informed at all by like the intelligent tutoring system? An intelligent tutoring system, because people are like completing problems, they're doing a math problem and they like have the wrong idea on how to do multiplication or something, they're going to probably consistently get the wrong answers and in the same way, kind of as you were describing.
Yeah, there's a number of areas where we think of people as holding beliefs, and we think about the sort of the role of the assistant as being to inform those beliefs. That particular subproblem has been studied. Even, you could describe my thesis work as doing that, because I did this whole thing about like, the person doesn't know something about the robot. So for the robot to be transparent, it has to essentially manipulate the person's belief to go converge to the correct parameters, right? So those aspects have been there, and it's essentially kind of what we're leveraging. But I think we're taking it this maybe a little bit of a step forward and saying this, thinking of people as then acting rationally based on that, and then their beliefs evolving is kind of how you can get predictive models of human behavior for collaboration. Is how you can, you can do all this other stuff about interaction that's not specifically about tutoring or transparency or shifting belief.
I have a quick question, actually.
Yeah.
So the case where you you model rationality but under false belief, can it just be captured with a different class of utility functions? So there's still utility maximizing agents, but the class of utilities change to capture.
Different? Yeah. So the thing about utilities is that if I let the utility function be expressive to capture the space of all possible functions you can define to represent the utility, then I can explain any policy as optimal, because I can sort of literally make the utility be like, this is the thing you have to do, period. So that's, for the most part, true. And so, in a sense, it's a bit of a red herring, because, like, yeah, we can represent everything as a policy. We can represent everything as like optimal respect to like utility that's completely unstructured, right? The question is more about, what can you have a reasonable prior and do the fine tuning on? So what kind of structure overall you're imposing in the kind of the architecture of the model that enables you to make robust predictions out of distribution. And kind of that goes back to the question over there of, well, you could do it in a number of ways. You could do it via just the utility and make the utility more flexible. That probably won't generalize very well. You could do it with fine tuning to, like, the example I was just showing. Optimal behavior prior basically says, I'm going to compute the optimal behavior. That's just going to be a prior. But if the underlying reason people deviate is because they make wrong assumptions about the dynamics, sort of understanding that and then being rational or noisy rational on top of that is going to generalize better than fine-tuning based on away from a rationality, sort of with just observing data. So that's sort of the game we're playing. And I don't know. I guess it's an ongoing topic, and I'm looking forward to sort of teaming up with some people in computational psychology and behavioral econ and see what they have to say. To the best of my knowledge, this is not how behavioral economists work, but maybe there's actually some papers there that I haven't found that are already looking at things like it. So this stuff is very fresh in my mind, and it's just how I've been recently thinking about the problem.
Cool, very interesting. Thank you.
Thank you.
Any last questions?
I think we're good. It's 34. Let's let
We
these
are
people
good,
go.
okay. Let's thank Anca again, and
Thank
thanks
you.
everyone for coming.